Once we have examined the scatter plot, the next step would be to quantify the relationship between the explanatory and the response variables. So when we try to use a line to model that relationship, we call it a linear regression. Linear regression assumes that the relationship between two variables x and y can be modeled by a straight line. So this would be y, ignore the hat there, so just cross that out. So y equals beta naught plus beta 1 times x. So again, this would be y equals beta naught plus beta 1 times x, where beta naught and beta 1 represent two model parameters for the intercept and slope. These parameters are estimated using data, and we write their point estimates as b naught and b1. It is rare for all of the data to fall on a straight line, as seen in the three scatter plots below. In each case, we have some uncertainty regarding our estimates of the model parameters beta naught and beta 1. For instance, we might wonder, should we move the line up or down a little? Or should we tilt it more or less? The graph below shows a scatter plot for the head length and total length of 104 brush-tail possums from Australia. Each point represents a single possum from the data. The highlighted point represents a possum with a head length of 94.1 millimeters and a total length of 89 centimeters. So remember that the x-axis is the explanatory variable, and the y-axis contains the response variable. Okay. Let's continue. So the head and total length variables are positively associated. While the relationship is not perfectly linear, it could be helpful to partially explain the connection between these two variables with a straight line. We want to describe the relationship between the head length and total length variables in the possum data set using a line. In this example, we will use the total length as the predictor variable x to predict a possum's head length y. There are many linear models we could use, some better than others. The best fitting model has the equation y hat equals 41 plus 0.6x. So where are these numbers coming from? The first number, 41, is the y-intercept. You can estimate it by extending the graph to include x equals 0 and look to see where the line crosses the y-axis. The second number, 0.6, is the slope. You can estimate it by approximating the rise and the run from one point on the line to the next. The slope will be the steepness of the line, rise over run. 6 divided by 10 is 0.6. We can use this line to discuss properties of possums. For instance, the equation predicts a possum with a total length of 80 centimeters. We'll have a head length of 89 millimeters. So replacing the x with 80 and typing this into our calculator, we would get 89. So that is, our prediction is that a possum with a total length of 80 centimeters will have a head length of about 89 millimeters. The hat on y is used to signify that this is a prediction. I'm going to underline that. This prediction may be viewed as an average. The equation predicts that possums with a total length of 80 centimeters will have an average head length of 89 millimeters. Absent further information about an 80 centimeter possum, the prediction for head length that uses the average is a reasonable estimate. We can use residuals to check the strength of our model. Residuals are the leftover variation in the data after accounting for the model fit. So residual equals data minus fit. We also can represent this as E equals Y minus Y hat. So if you take a look at this plus sign here, which we can call a data point, so this is Y, then the residual would be the distance between that and the line. And so the place on the line is Y hat. It's the prediction. So the actual data value minus the predicted value equals the residual. Every observation will have a residual. Observations above the prediction line will have positive residuals, or in other words, we underpredict. They have underpredictions with that line. Observations below the line have negative residuals. In other words, the line has an overprediction for those values. Here's example 6. The linear fit shown below is given as y hat equals 41 plus 0.6x. Based on this line, formally compute the residual of the observation 77.0, 85.3. This observation is denoted by x on the plot. So we would take 41 plus 0.6 times the x value, 77.0. This gives us an answer of 87.2. This is the prediction. Or in other words, this is y hat. 85.3 minus 87.2. So I take the actual data value, y value 85.3, minus the prediction y value 87.2, and I get an answer of negative 1.9. This is called the residual. Here's example 7. If a model underestimates an observation, will the residual be positive or negative? What about if it overestimates the observation? So y minus y hat, if that equals a positive value, that means that the model underestimated it. If y minus y hat equals negative, a negative value, this means that the model overestimated it. Residuals are helpful in evaluating how well a linear model fits a data set. We often display them in a residual plot, such as the one below. So in the scatter plot, every data point has an x-coordinate and a y-coordinate, which is the total length in centimeters, comma, the head length in millimeters. On a residual plot, each point has an ordered pair x, comma, y minus y hat. So it's still the total length, comma, but then it's the difference between the actual data value and the predicted data value for the y-coordinate. The residuals are plotted at their original horizontal locations, but with the residual on the vertical. For instance, the point 85.0, 98.6, which is this one here, has a residual of 7.45. So in the residual plot, it is placed at 85.0, 7.45. Creating a residual plot is like tipping the scatter plot over so the regression line is horizontal. Here's example 8. One purpose of residual plots is to identify characteristics or patterns still apparent in the data after fitting a model. The figure below shows 3 scatter plots with linear models in the first row and residual plots in the second row. Can you identify any patterns remaining in the residuals? So I'm looking at the first one and its residual plot. So concerning the residual plot, everything seems to stay within a band. So I could draw like this bandwidth around all of the data points, and they all seem to stay within that bandwidth. So we say that there is no pattern in the residual plot, which is a good thing. For the second one, we see that there is actually a curve in the residual plot. And that's not good. It means that the linear model is not a good fit. For the last one, we can also see that there is also no real pattern in the residual plot, so I could draw this bandwidth again. All the data seems to stay within that. So, no real pattern here, which is also good. But we can also see that for a linear model, this relationship is pretty weak.